Rodrigo, bonjour.
Bonjour.
Alors, on m'a demandé de te présenter. So let me say the following. It's a pleasure to meet Rodrigo. It's the first time we meet, actually. But he's been working with almost all my friends in France in particular.
Yes.
And I would have loved to have him for a prolonged period of time in Montreal, but somehow the luck has made it that he'll be, God permit, coming to Manitoba, to Canada, in the near future. As soon, I suppose, as traveling becomes possible. So it's a pleasure. I wish to thank you, Rodrigo, for agreeing to do this talk on very short notice, and we're eager to listen to you about the title that is on the screen. So thanks again.
Thank you, Luke. So please go ahead.
All right, so thank you, Luke, for this nice introduction. Okay, so let me start. Thank you very much for the opportunity of presenting this work here. So it was done with Francisco Alcaraz from the University of São Paulo, and it's about some new family of integrable quantum spin chains with free fermionic and parafermionic spectrum. Right? And you may find more details in these two archive preprints. Okay, so let me start by defining what we are calling free fermions. And it's actually a quite simple definition. So we have some Hamiltonian whose spectrum can be written in this way. So we have some quasi-energies, say epsilon 1, epsilon 2, up to epsilon L. And each quasi-energy contributes with the eigenvalue of the Hamiltonian with a plus sign or a minus sign. And they are independent of each other. And so in such a case, we would have 2 to the L possibilities here. Okay, so this is quite common. And maybe what is not so common is that this notion can be generalized to system with more than 2 states. So for two systems with any states. So what we do, we still have some quasi-energies like this, epsilon 1, epsilon 2, and epsilon L. And now we replace the plus minus signs by an omega 2s. So omega is a root of unit, and s can go from 0, 1, 2, up to n minus 1. And
so you don't have a Hermitian Hamiltonian.
Yeah, so it's not Hermitian for n bigger than 2. Yes, in fact. Okay. And so one nice way to see this parafermionic structure is the following. So it's some kind of exclusion circle that generalizes the Pauli principle. So what we do?
Excuse me, Rodrigo. I don't know. There's a lot of noise. Is it at your end, or someone's mic is still open? I don't know if you could do something, but it's a little difficult to listen to you.
Okay, so I will put my microphone close to my mouth. Maybe it's better now.
Yeah, maybe, yes.
Okay. Okay, so the idea is the following. So let's take an example, n equals 3 and 3 sides. And let's, for each quasi-energy, we draw some circles like this. And for each s, we draw some branches like this, s equals 0, s equals 1, and s equals 2. And we put particles, quasi-particles in these circles. And there cannot be more, they cannot be at more than one place. So for example, 0, 0, 0, we have all the quasi-particles at this axis. And for 1, 0, 2, we have a particle in the first circle, and we have a quasi-particle in the second circle, and the third one in the third circle at this position, okay? And so here, for example, we would have 27 such diagrams, right? And let me mention some examples of Hamiltonians that has this kind of spectrum. So the first one is the Ising model in a transverse field. It is a very famous and important model. So here is the Hamiltonian. We have the interaction, we have the potential term, sigma z, and the transverse field. And as it's very well known, this model can be solved via Jordan-Wigner transformation. So the idea is that we replace the spin variables to some fermionic variables, like this. And by doing this, we can write the Hamiltonian in terms of bilinear in the fermions, okay? And so this is a feature that tells you that this Hamiltonian has a free fermionic spectrum, okay? And let me just mention that in the homogeneous case,
Sorry, in your fermionic, usually one has creation and annihilation. You only have creation.
But here,
or the odd one somehow.
Here it's Majorana fermions. And so the psi dagger is equals to psi, right? Okay, and so in the homogeneous case where all the couplings lambdas are equals to 1, we actually know an explicit solution for the quasi-energies, and they are given by this formula. Okay, and so for n bigger than 2, there is this very nice model that was introduced by Baxter in the late 80s. And the idea is the following. So we introduce a Weyl pair, which is a generalization of the polymatrices. So we have big Z and big X, and they omega commute. And the power to n of X to n and Z to n is equals to 1. And the Hermitian conjugate is Zn minus 1, right? And so just as an example, for n equals 3, here are the X and Z. So they are 3 by 3 matrices. And we know these matrices for n, okay? And the Baxter model is nothing but a direct generalization of the Ising model in a transverse field where we replace the Pauli matrices, say sigma Z by big Z and sigma X by big X, okay? And although it's a very direct generalization of the Ising chain, Baxter found this model in a quite sophisticated framework that involves the Tau2 model, the Kiralpot 6 vertex, and the Baxter 4 spin, and so on. And he observed numerically that the spectrum of this Hamiltonian has the form I mentioned. So it has a free parafermionic form. And until very recently, this was the only model with such kind of spectrum, right? And let me mention that if we add the Hermitian conjugate term here, the model is no longer free, although it would have a real spectrum, but it would no longer be a free spectrum. Okay. And Baxter in his paper he asks how we could prove this result, because we should expect some very similar way to the way the Ising model is solved, because it's just a direct generalization, but it's not the case. So, and what happens is the following. So if we try to apply the Fredkin-Kadanoff transformation, we get a Hamiltonian that it's not quadratic in the Majorana parafermions, because the psi dagger now it's proportional to psi to n minus 1. Right? So the Jordan-Wigner technology doesn't work in this case. And actually, this result was proved by Tarasov using the quantum-inverse scattering method in the beginning of the 90s. And also, and Baxter also recovers the same kind of result using functional equations similar to what we are going to do here. And only in 2013, finally, Paul Fendley finally solves this problem using a parafermionic language, right? So it took quite a while to someone be able to solve this problem in a parafermionic language, right? And the last example I would like to mention is a model that was introduced by the same Paul in 2019 in this very beautiful paper called The Free Ferms in Disguise. And the Hamiltonian is quite simple. So here is this expression of the Hamiltonian, and it has three body interactions. And we can try to apply the Jordan-Wigner transformation to this Hamiltonian, and what we are going to get is an expression like this. So it's an expression of order 4 in the fermions, okay? And so it's quite surprising that this Hamiltonian has a free spectrum, all right?
So
And,
why is it order 4, not order 6?
You just have to apply and it will cancel. And yes, it's order 4 because there's some accent, they combine and collapse to 1. So I think it's really order 4. Okay.
There's
It's all right.
Some anti-commutator or something? Maybe
Yes.
there's an anti-commutator coming in.
Yeah, I guess, yes. Yeah. Let me think of it. Yeah, I think I did this exercise and I think I've really found order 4. And so it's, we may notice that it's not, so there is a jump here, okay? So if here it was a plus 2 and a plus 3, this would not be free fermionic. All right. Okay, so we may ask then what all these models share, and because this example shows that being of order 2 is not a necessary condition to obtain a free-form spectrum, and the answer is actually the fact that the energy density operators satisfies a very simple algebra. Okay, and this algebra is so let's take again the Eisenbachster model. And let's write it as a sum of generators, H1, H2, up to Hn. And so we say that the odd generators are big X, or the polymatrix sigma X. And generators are the Z dagger term. We would have 2L minus 1 generators. And we can easily check that they satisfy the following algebra. So the neighbors omega commute, and if they are far away, they commute, and the power of the generators collapse to the identity. Okay, so this is just an observation, which is valid, of course, if n equals 2, this omega is minus 1, so the generators anti-commute. Okay, and similar thing happens with the Bentley model. So we take the generator to be this product of sigma matrices, sigma z, sigma x, and sigma x. And now we can check that the not only the neighbors, but also the next neighbors anti-commute. Okay, and they will only commute if the distance is bigger than 2. And again, we have that the power collapse to the identity, okay? And so what we propose is that these algebras can be extended to arbitrary n and p, where p is some integer bigger than 1. And the algebra is the following. So the first p neighbors omega commute, and they omega commute up to p, and they commute if the distance is bigger than p. And again, the power collapses to the identity. And the claim is that the Hamiltonians built from this algebra have a free parafermionic spectrum. Okay. And so, so any question up to here? Okay, and so let me just, so we can easily build representations of this algebra. And so, for example, for p equals 1, this is a representation, just zx. And for p equals 2, we would have zzx. And for p equals 3, we would have zx, and so on. And so this parameter p measure how many body we have in the interaction. Okay, but actually we are going to perform the diagonalization of these Hamiltonians independently of the representation. Okay, and so the question is how to solve these Hamiltonians, because the Jordan-Wigner transformation does not apply in general. And the idea is to exploit integrability, all right? And so the key point is that this algebra allows us to build a set of mutually commuting charges. And then, okay, so the algebra is so simple that it allows us to build explicitly many conservative charges, right? So we use ideas from the paper from Boxer and Finley. Okay, so the program is as follows. So I will show you how to build charts, operators that commute with the Hamiltonian. Then we will assemble a generating function of these charts, which is just this somehow algebraic polynomial. And thanks to very remarkable properties of these charts, the generating function satisfies a very amazing formula. So we take the product of all these generating functions, of any of these generating functions, and they collapse to the identity on the right-hand side, right? And it also follows that these polynomials here, they will be given by a recurrence relation of order p plus 1. So it's of second order only if p equals 1. And by using this inversion formula, we can actually find the eigenvalues of all the charts. And they are given in terms of the roots of the p polynomials. Okay. So this is the idea, and let me show you more in details how it works.
Sorry, I think I missed something. The degree of the polynomial is the index on P?
So here it's the...
Yeah. And so the G's are linear in the U's?
Sorry?
The G's are linear in the U's?
No. The G's are...
So then I don't quite understand.
The G's are
M and M tilde. So M tilde... I don't know.
Okay, I will define it more precisely in a minute.
No, but I mean, you have something funny in that box because the running index is, okay, so I don't know what M tilde is. M bar.
Okay, so I will define it soon.
Okay.
Here it's just to give an overview of what we're going to do, right? So I will define more precisely everything.
So big M is just M times M bar.
Yeah, M is the number of generators. Okay, so
and each one is a polynomial of degree M bar. So.
Yeah. Okay, M bar it's an integer part of. Let me see. Okay, so
the
here
degree of P is the product of M and N bar. Is that correct?
The degree of P. The degree of P is M bar.
N times M bar.
Yeah.
Okay.
Okay, so the idea to build the charts is the following. So we have this set of M generators, H1 up to Hm, and we take a subset of this set with N mutually commute elements and build a string from them, okay, like H to J1 up to H to J. Okay. And we sum all the possibilities, and then we get a chart. And so let me explain better what this means. So here are the charts. So the first charge is nothing but the Hamiltonian, so the sum of generators. And the second charge is built from elements that have two generators, and so on up to m bar. So m bar is the integer part of this quantity here. So this is the number of charges that we can build is m bar. Okay, it's the maximum number of such kind of elements we have for a given m and a. All right. And just to be more clear, let me give some example. So let's take p equals 1, m equals 3, and so m bar is going to be 2. So we have two charges. So the first charge is just the sum of generators, and the second charge, we see that the only product that we can form where all the elements are mutually commuting is H1 and H3. So these are the two charges. And only using this algebra, we can show that they commute. Okay. And so let's say the p equals 1, m equals 5. Now m bar is equal to 3. And so here are all the charts. So the first one is again the sum of generators. And to build the second one, we take pairs. So like H1, H3, they commute. H1, H4, H1, H5, and so on. So with H2, it commutes with H4 and H5, and H3 commutes with H5. So in this way, we form the second charge. Okay. And the last charge is we need three H operators. And so the only possibility is H1, H3, and H5. Okay. And so we can, again, only using this algebra, we can show that they are all mutually commuting. All right. And the last example, let's just take b equals 2 and m equals 4. Here, m bar is 2 again. And so we have two charts. The first one is the sum of generators, but now we have to jump two generators. So the second charge, it's the only possibility is H1 and H4. Okay.
So just to recall, the HIs are monomials in the fermionic operators?
In the H generators. Okay.
The H's are, yeah. The little h's, how are they expressed in terms of the fermions?
Okay, so in general, I don't know, but I think certainly you can do it. But what is important is that they satisfy this algebra. But indeed, you can find representations in terms of the fermionic operators.
Can you just recall the definition of the little h's?
So here it's the definition. Right?
Well, that's relations. What is the definition?
So the algebra is defined by these relations. Okay, so an example of representation is like this one.
This is what I'm asking. So you've got these as monomials in the spin operators. They could also be in the fermion, in the Majorana operators.
Yes, indeed. Yes. But in principle, actually, so actually we don't need to use representations to diagonalize this object. At least at I mean, if we at least at the spectral level, we don't need. Okay, maybe after if we want to build eigenvectors and so on, then we will need to use some explicit representations. But to get the eigenvalues, all we need is the algebra. Okay.
Well, I don't understand that at all. I mean, simply knowing the algebra doesn't tell you what your module is or what. So how can you get the eigenvalues? You need to know what space it's acting on.
Okay, so just give me a moment and I will try to convince you. Okay, it's some kind of algebraic diagonalization. All right, so okay, so any questions about the charts? So I hope it's more or less clear. Okay, so the step 2. So we take these charts and we build this polynomial. Okay, so the GM is a polynomial in U of the whose coefficients are the chars, the generators. Okay, and it follows that these chars, in the way we defined them, they satisfy a very remarkable recurrence relation. So the charge M can be generated by the charge M minus 1 and by the charge M minus P plus 1. And this also implies that the generating function itself also satisfies a recurrence relation. Okay, it is given by this formula here. So these are very two important properties of the charts and of the generating function. Okay, and by only using this, we can in fact show that they satisfy these properties. Okay, so the generating functions, they commute for different values of the spectral parameter, and that's why we say that these models are integrable. Okay, and I'm not going to show details on how we can prove this, but the idea is that we use these two relations and use induction. Okay, and okay, so the third step is the following. So we take a product of these generating functions. So it's a product of n terms, and we can also show that they collapse to the identity. Okay, the proof of this is a bit more complicated, and so we have done it for n equals 2 and 3, and we could do for n bigger than 3, but it starts to get complicated, but in principle it can be done. Okay. And the idea to prove it is to show that this product that we call tau m, it also satisfies a recurrence relation that it's very similar to the recurrence relation of the generating function itself. Okay. And so let me give another example just to make things clear. So we take n equals 2, p equals 1, and m equals 3. And the G3 is the following. So it's the identity minus 1, the charge 1, plus U2, the charge 2. Okay. And we just take this product. For n equals 2, we have two terms. So G of U, G of minus U. And we write all the terms, and we use the algebra. And then we see that this miracle happens. So all terms disappear, and we are left only with the identity. Okay. And so this kind of formula is known as the inversion relation when n equals 2. And it also follows from this formula that this polynomial, which is going to be very important for us, these polynomials, they are also given by a recurrence relation of order p plus 1. And so here we use this u to the n as z. And so this is the defining relations of these polynomials. Okay. And okay, so so how we solve this problem then? So let's take again the n equals 2. So we have the product of the two generating functions, and they collapse to the identity. And since they commute for different values of the spectral parameter, we can find a common basis. Let's say psi, whose eigenvalue is lambda of u, and we apply this this function on psi, and we obtain a formula for the eigenvalues of g. Okay, so the formula is this one. So lambda of u times lambda of minus u is this polynomial of u squared. Okay, and in a similar way, so with this generalized to n states, right? So we have this product of any lambdas is equal to this polynomial, and we may write this polynomial in this way, okay, in terms of the roots, zi. All right, and so actually by writing in this way, we can easily convince ourselves that the solution to this functional equation is the following. So the lambda m of u is just a product of u minus u, the omegas. So here there should be a set of s's. So there are many possible solutions for this functional equation here. And they are all given in terms of the roots of the p polynomial that we can write in this nice way, okay? Where the epsilon I are the zi to minus 1 over n. So the epsilon I are the quasi-energies that I mentioned in the beginning. Okay. So we see that the spectrum of the generating function is directly given by the roots of the p polynomial, right?
Rodrigo, for the last step, this step, usually I've seen other teams doing the solution of the previous slide, the one just before, yeah. So you have, no, this one, yeah. Is there a single solution of way of attributing the various zeros of the u to a given capital lambda? For example, I mean, passing from this slide to the next one, it's like, yeah, exactly. It's taking the nth root for the lambda. Is there a single way to do that?
Yes, I think so, because we are parameterizing the solutions by these SIs, right? So here we make a choice of sign. So we choose the u to be the zi up to 1 over n. And for each set of s's, we have a solution of this lambda. So actually we have n to the s solutions, right? To this functional equation.
So this lambda is not unique. There are several capital lambda that would work.
Yes. And what is actually expected, because so the Hamiltonian has many eigenvalues, right? So the generating function is also expected to have many eigenvalues.
Thank you.
Okay, and so we can just write this this product using the Vieta theorem. So we expand the lambda in terms of u, and here we have the elementary symmetrical polynomials. And on the other hand, we also know that the transfer matrix, the generating function is a sum of charts. And so we just compare and we find all the eigenvalues of all the charts. Okay. And in particular of the Hamiltonian, it's given by the E1. And so it's this form here, okay, which is the form I showed you in the first slide. All right. And so here, so we see that we diagonalized the Hamiltonian without independently of the representation. Okay, so let me speak a little bit about this polynomial. So it's a very important polynomial, because essentially all we have to do is to compute the roots of this polynomial. And so when we found this relation, so so I'm going to take the couplings to be the identity now. And so what we really did, we plotted some cases, and maybe for some people it could be obvious, but we took some time to find the explicit solutions of these polynomials. And so we found that they are given by this formula when all the lambdas are equals to 1. Okay, and we also found a formula when the lambdas are arbitrary. Okay, and so here is the explicit formula. And if you recall the charts, they are actually very similar to the charts in terms of the generators. It's essentially the same formula, but we replace each generator by a lambda 2n. Okay. And let me just mention that for p equals 1, So these polynomials are the Chebyshev polynomials of second kind. And but for p bigger than 1, we don't know if they have some special name or not. Okay, or we also don't know if they are orthogonal or not. Okay, okay, what we can also do, I will skip the details on this part, but by using some tricks, we can actually find some parameterizations, some parameterization for the roots of these polynomials when I'm considering now lambda equal 1, all the couplings, and so I am in the homogeneous case. And so we can find this parameterization for the roots of these polynomials. And this pk is some kind of momentum that is subject to some quantization condition. Okay, but this quantization condition is only exact for p equals 1. So for p equals 1, we know this explicit form, but for p bigger than 1, things starts to get complicated. So we have this kind of quantization condition, and this is valid only when m is big. And even in this case, we don't know how to solve this explicitly, but we don't need it. Okay, but nevertheless, what we can do, so let's say we want to compute the ground state. So the ground state is going to be given by the case where all the s's are equals to 0. And so it's just this sum. And if you recall, these epsilons are, say, the square root of the, like epsilon 1 is 1 over z1 to 1 over n. And so to compute the ground state of this these spin chains, what we have to do is to compute all the roots of the polynomials. And we have observed that the based on the p equals 1 case, where we know the explicit quantization solution, we observed that actually the root density, it's also valid for any p when for large m. And this allows us to write the ground state in this way. So we define the ground state over n. N is like the length of the chain, and we can convert it to an integral. And by doing this change of variables, we have found some closed forms for the ground state. So for p equals 1, here is the formula. So it's given in terms of the gamma functions. It's missing a gamma here. And this result was known before. For the Ising case, it's -2 over pi. And for the Baxter, for generic M, it was found more or less recently, in 2017. And for p bigger than 1, we start to have some nice functions. So for p equals 2, we have the f21. For p equals 3, we have this Appel function. And for p bigger than 3, we start to have this Lauricella series. I think they don't have a name after 3, okay? And one nice thing we can also compute is the gap to the ground state. And in particular, the gap we can compute very efficiently. Why? Because the gap is proportional to the largest, to the smallest quasi-energy, and it corresponds to the largest root of the polynomial. So we can use some bounds, like we have been using the Laguerre bound, and so we can compute very efficiently the gap to the ground state. And so in particular, we have determined how it varies with m with a given critical exponent. Okay, and so here is so we have observed that this critical exponent goes like this: p plus 1 over n. And in this table, we put some numerics and compare it with exact values. So we have found a very nice agreement in both in the ground state and in the computation. This. And so what we would like to do now And so the first thing is to find a way to build the raising and lowering operators. So because the Jordan-Wigner does not apply anymore, so this is not a trivial task. And after this is done, we should be able to compute correlations and maybe entanglement entropy. So I would like to study this paper very carefully. Maybe the results here can be extended for these new free fermionic systems. Right? Another very interesting case is the, maybe I didn't put enough emphasis, but all the spin chains I spoke about, they are open chains. And when we try to close the spin chain, it's a new word emerges because the inversion relation or the product formula is no longer valid. So it's quite surprising, but it's much, much harder to solve the periodic case. Right? And I think it's still an open problem. And one nice thing I think we can do, at least numerically, is to consider the random coupling case. So because as I mentioned, the gap can be computed very efficiently. And so we could we can run many samples and we can find distributions of the gaps following this paper, for example. And also, we may ask if there are new integrable structures to be discovered, because we know that the Ising case, which is P equals 1, N equals 2, it's connected to Onsager algebra, Tempere-Lieb algebra, Yagi-Baxter algebra, and it seems that this is not the case for any other values of N and P. So I'm pretty sure that there are many nice things to be discovered here. Okay, that was it. Thank you.
Thank you very much. So I open the floor for questions, please.
So I have a question. So do you hear me?
Yes.
Yeah. So nice talk. I could only catch the last part. Sorry. So have you tried for periodic chains to get the gap numerically and see if this exponent, this critical exponent ZC changes with the boundary condition or not?
We are not quite there yet, because what happens is that, let me go back here. Okay, so this breaks. Okay, so we can build the charts. So far, we have not yet proved that they commute, but we have made many checks. So the integrability part should remain. It should be okay. But then we try to compute the same kind of product. So we again have some nice polynomial here, but we have some extra operator here, some O operator, let's say. And this operator has eigenvalues, and I mean, it's not clear what to do, because one thing is that this operator commutes with the transfer matrix, so we could go to some kind of basis, a common basis, but then there are selection rules, and so it's I still have hope, but it's not so easy as I would like to see.
But I meant like by brute force. Like, can you even write down the spin chain Hamiltonian, and then just using?
I mean, if you just take this Baxter chain.
Yeah. Yeah, exactly. Because you have some form from the Hamiltonian, and then you can run DMRG or exact generalization.
Yes.
Without solving anything analytically, just brute force or almost brute force, and try to see how the gap scales with system size for small sizes. So it's very unmathematical in some sense, but just to explore.
Yes. The problem is that this Hamiltonian is quite big, and we can't go too far using an explicit representation. And actually, for this specific one, there is a paper by Alcaraz Liu and Bachelor that I mentioned. No, sorry, by Alcaraz and Bachelor, that they studied this this chain, the Baxter chain with periodic boundary conditions, and they found a quite unusual book behavior. So the book behavior seems to depend strongly on the on this boundary condition, but I don't remember if they computed this Z. I don't think they computed. Yeah, but okay. So what I wanted to say is that okay, there can be some numerics could be done here, but for the Fendley chain, for example, I think it's no one has looked at it for the moment. But indeed, we could do some numerics.
Mm-hmm. And I saw that you had some Z exponents that were below 1 in your table for different values of P and large N. And well, to me, it's fairly unusual. I don't see Z above 1 very often. 1 is the sort of usually conformal spin chains, and 2 is common. But below 1, like 2/3 and 3/4, is that? Are there other examples, or is this somehow?
Okay, so for n bigger than 2, so these models here, they are not Hermitian. So there's this sketch. So I'm not quite sure what this really means there. But even for n equals 2, we have some different exponents as well.
Okay, but so then they're above, but these are 1 or above, so they pass my sanity check that you don't have below conformal. But the other ones, you say they're a non-Hermitian, okay. Okay. And the first one is the n equal 2 and p equal 1 is a CFT, right? I mean, I forget.
Yes, yes. Yeah. This is the isomorphism.
Yeah, perfect. Thank you.
So Fendley found these 3 halves. Mm-hmm. I think this is related to KPZ.
Yeah.
But there's others.
Mm-hmm. The 5 halves. That's especially. Does Paul have any ideas about what's described by this 5 half? No. Okay. For future work. Thank you.
Thank you. Any other questions?
Is there anything like our matrix Yang-Baxter type structure behind these?
Yes, for sure, for n equals 2 and p equals 1. So you can kind of Baxterize this algebra, for example. And okay, so let me say first. I'm going to speak about p equals 1 first. So this case, and this case. So for p equals 1, n equals 2. I mean, for p equals 1 and arbitrary n, this is related to this tau2 model. And so you do have an R matrix, which is the 6-vertex R matrix, which intertwines a Lax operator that involves this Z and big Z and big X. And you could also Baxterize, and now only for n equals 2, p equals 1, you could Baxterize these generators. So this works. But for p bigger than 1, even when n equals 2, I think it's a new word to be discovered. Yeah, I also think you can Baxterize, but now, you know, you would have you would have like an so when you Baxterize, you have like an Ri plus 1 Ri equals to ... the standard Yang-Baxter equation. And now you would have this one, but you would also have Ri 5 plus 2, Ri equals to blah, blah, blah. So you have two kind of structures for P equals 2, for example. And I don't know how to build all the quantum-inverse scalar method for it, but I think it's a very interesting problem to be looked at.
Luke, please go ahead.
Okay. Well, thank you, Rodrigo. This was a very interesting talk and beautifully crafted. Two questions maybe. Did you explore, to John's point, did you explore somehow I know you did not need it to diagonalize, but nevertheless to obtain specific realization, did you study a bit the representation theory of the algebra you define?
We didn't. So actually, we do build some representations, and we see that when we choose some specific representations, some degeneracy appears. And so for some specific representations, we could build additional charts that account for this degeneracy. But in general, I don't know how to handle it. But it should be somehow simple because they are all the same degeneracy. All the levels always have the same degeneracy. So it should be some simple stuff going on. But I don't know.
My other question, well, you were kind enough to cite our paper, but in that paper, a critical element was well, we were using orthogonal polynomial, but what's really critical is the bispectrality, is the fact that you have a pair of operators connected to the polynomials in question. So I understood that you have some kind of recurrence relation for your critical polynomial P, but does it satisfy? Do you have a differential equation of some kind, or do you have such a bispectral feature?
Well, I expect that we will do have this kind of property, but I'm not sure if so there you have this three diagonal matrix, right?
Yeah,
so
but this is required for orthogonal polynomials, but this is not a necessity to proceed with the construction of a matrix that would commute with the correlation matrix. You could use a five diagonal realization and so on. So just to mention that, but you need to have a duality because you want to chop in space and in energy. So this is where you need to control two spectra. And so this is.
I think we will have such kind of thing, but the relations are not of second order. Okay. I'm not sure how critical that would be.
And has any of that been done in either in the Baxter or in the Fendley model, more specifically?
No, I don't think so. I don't think so, because I mean, one thing it has to be better understood is how to build the raising and lowering operators. And so Fendley proposed a very nice formula given in terms of this generating function and some additional generator that he calls an edge generator, but I haven't studied it very deeply yet. So I mean, we do, and we observed that this formula he proposed actually extends for NP and NN, but how to use it, it's not clear yet. Right. And after that, so I start to look the correlations and then the entanglement, entropy, and so on.
Thank you very much.
Any other questions from the audience? Well, if there's no other questions, I'd like to have one question. And if you could go back to the charges that you defined, the capital HI, those kind of like I almost want to refer to them as selective symmetric polynomials, which are like, there are these selected monomials that you sum up together. And I was just thinking from the point of view, from the perspective of symmetric functions, is there any, like, what I see is that it's almost like you have your labels as nodes in a graph, and let's say you consider a graph that is that has a simple definition attached to the algebra, in which if two elements are commuting, then their corresponding labels are connected, and otherwise there's no connection. And it's almost like you construct a selective sort of structure of symmetric polynomials for each order. And I'm wondering if there would be a generalization in this direction. This is just completely just trying to see what kind of general structure lie behind.
Yeah, I tried to search the literature for these kind of things, because indeed I noticed that even if you take the explicit yes, like here for the polynomials. So you have this kind of, as you said, some symmetrical polynomials where you miss some parts, but I didn't find anything. But maybe I just don't know how to search.
Just looks very intriguing, these kind of like, interesting monomial sums given all these conditions on the. Okay, very good.
And even in the case where all the lambdas are equal to 1, I tried to see if these polynomials are orthogonal, but I couldn't find an answer yet, because most of the orthogonal polynomials that we know, they are second order. And here, for p bigger than 1, they are higher order. And I'm not sure if this is a if and only if condition. I mean, does every orthogonal polynomial has to be given by a second order, or you have examples of orthogonal polynomials that are of higher orders?
What do you call the order? The order of the recurrence relation? Is this what you?
Yes.
Yeah, no, the orthogonal polynomials in a single variable must satisfy a three-term recurrence contiguous. So m plus 1, m and m minus 1. But you could you could cast them, but this does not look symmetric, into a matrix orthogonal polynomial if the recurrence relation is of higher order, or there are more, there are bi-orthogonal polynomials or d-orthogonal polynomials. So there's room for to play with objects that are more known. But the three-term, the classical orthogonal polynomials, they must satisfy the so-called Favart theorem, right? So it has to be a three-term m plus 1, m, and m minus 1.
Yeah, one thing I checked is that for p equals 1, so we can write these polynomials as a determinant of a three-diagonal matrix, right? Like, and for p equals 2, it's also a three-diagonal matrix, but you jump one diagonal. So like you have one diagonal, the main diagonal, and for p equals 1, the diagonal below the main diagonal is full. For p equals 2, you jump one.
Okay.
For p equals 3, you jump another one, and so on.
Interesting.
Okay, so these are for sure not orthogonal polynomials for p bigger than 1.
Is it a statement or a question?
A question.
Yeah, I can say that definitely they are not orthogonal polynomials. These are new objects. It's sure. But I can say that when p equal to 1, these objects resemble so-called Tilly polynomials, which were described in my paper together with Satoshi Tsuchimoto and some other people. So you can just look at Frobenius, Stickel, Berger, Tilly polynomials.
For arbitrary lambda, you say?
Yes, yes, exactly. Even more, in our paper, it was one more parameter, just when p equal to 1.
Okay, can you please repeat Frobenius?
Frobenius, Stickel, Berger, Tilly, three names. This FST, so you can find by this abbreviation, FST polynomials.
But maybe, Alexei, you could send Rodrigo your
Yeah, I can send, of course. Yeah.
Very good. Okay, so anything else? If not, then let's thank the speaker for this great talk. Thank you very much. And we'll reconvene next week. Okay.
Thank you very much for the opportunity.
Thank you very much, Rodrigo. Hope to see
Bye.
you soon.
Hope to see you soon too.
Take care.